The James Webb Space Telescope has discovered something truly extraordinary: beams of light that appear to be radiating from a city center, shining from a location light years away. This discovery has reignited interest in the possibility of extraterrestrial life. The telescope's focus was set toward Proxima Centauri and the closest exoplanet, Proxima Centauri b. It observed odd, brilliant flashes of light, which could be an indication of an alien civilization. Scientists urge the public to keep an eye out for more advancements. Over the years, both scientists and the general public have been captivated by the idea that there is life beyond Earth. Any indication of the presence of life in space has marked a pivotal moment in space exploration. One such moment occurred when the James Webb Space Telescope was built. It presented clear proof suggesting the existence of life somewhere in the universe. While scanning the depths of the cosmos, the telescope discovered an extraordinary event on an exoplanet. Because it was so far away, it only detected lights that resembled extraterrestrial design cities, raising the possibility that an alien metropolis might exist on that distant planet. This concept has sparked significant curiosity and excitement within the scientific community, as it could be the long-awaited breakthrough. It suggests the existence of intelligent, functioning civilizations, something we are only beginning to investigate. These lights resemble those of a large city, located 4 light-years away. At this moment, NASA engineers are amazed and perplexed by how long these lights might have been visible in space, just waiting for our technology to catch up. David Kipping, an astronomer at Columbia University, described the planet where these lights originated as especially unique. Unlike most rocky planets, it is intricate. It absorbs the sun's energy and releases it as ultraviolet light. This exoplanet behaves differently due to its relationship with its host star, Proxima Centauri, also referred to as Andia. The James Webb Space Telescope's ability to capture infrared wavelengths was crucial in spotting the unusual behavior of Proxima Centauri b. This is essential for understanding the planet's atmospheric conditions. Researchers plan to continue using the telescope to investigate the planet's atmosphere in greater detail, hoping to determine whether Proxima Centauri b is habitable. The telescope's high sensitivity to infrared light allows it to see even during nighttime events on Proxima Centauri b, where many other telescopes struggle to discern faint light in the vast void of space. Where the Webb telescope shines is in recognizing even the tiniest glimmers. This makes it an excellent confirmation tool. If the alleged city lights are indeed real, visible on the dark sides of Proxima b, artificial light can be detected by the telescope, as long as it falls within a specific, narrow frequency range, much smaller than that of normal starlight. Proxima Centauri b interacts with its star in a way that significantly influences its surroundings. Like many orbiting planets, it captures a powerful force from its star, going through day and night cycles similar to Earth. The planet experiences cooler daytime temperatures and significantly colder nighttime conditions. This thermal variation is significant to astronomers, as it provides useful hints about the planet's atmosphere. If the planet has an atmosphere, the temperature difference between day and night would be extremely hot on one side and chilly on the other. This thermal variation gives astronomers clues about the composition of the atmosphere. The James Webb Space Telescope can take images in the infrared spectrum, allowing scientists to examine global heat emissions and reveal interesting properties, including atmospheric details. The telescope is in Earth's orbit and observes Proxima Centauri b consistently. If its night cycle occurs every 11.2 Earth days, the next step is to investigate the chemical makeup of its atmosphere to determine whether it could support life. Detecting components like methane, water vapor, or oxygen would imply that the planet might harbor life. However, studying the light that passes through a planet's atmosphere is a difficult process. While the James Webb Space Telescope is excellent for describing planetary atmospheres, its design is mainly focused on analyzing carbon dioxide, water vapor, and methane. It is less adept at detecting free oxygen, a key indicator of life. Nevertheless, it can still look for other vital markers, such as ozone, which suggests a stable environment. As scientists analyze the data collected from the James Webb Space Telescope, the search for distant worlds continues. We are getting closer to addressing the question of whether or not we are alone in the universe. It's important to note that the James Webb Space Telescope can only observe a limited number of nearby exoplanets. For more in-depth examinations, astronomers will also use ground-based observatories, like the Extremely Large Telescope, ELT, which is expected to become operational in the 2030s. The ELT is designed to provide a closer look at exoplanet atmospheres and to reveal more about their potential to support life. Until then, telescopes like the ELT and the James Webb Space Telescope remain invaluable for locating distant exoplanets. Despite its limitations, the Webb telescope continues to provide vital information that could reshape our understanding of what lies beyond our solar system. Scientists have ambitious plans for future space telescopes, aiming to develop technologies that reduce interference from starlight. This would allow for better observation of planets in orbit. One method is similar to using your hand to block out the sun in order to see something more clearly. These future telescopes would be able to concentrate on the dim light reflected by exoplanets, making it easier to analyze their atmospheres and determine whether they could sustain life. However, this is no easy task. Stars are extremely bright and often outshine the planets around them, making it difficult to detect the faint light reflected by these planets. To solve this problem, scientists are developing several innovative strategies. One such method involves the use of coronagraphs, devices inside telescopes that block out starlight while allowing planet light to pass through. By carefully shaping the light waves, coronagraphs can significantly reduce the star's brightness, making it easier to detect the dim light from orbiting planets. Another promising approach involves using star shades, large, flower-shaped spacecraft that block starlight before it even reaches the telescope. This allows the exoplanet's light to enter instruments without interference. This technique is especially useful for observing planets in habitable zones, where water and liquid could exist, and where life may be possible. Modern technologies like star shades require exceptional precision. Their alignment must be accurate to the millimeter over long distances. These innovations must also overcome the challenges of space missions, including the need for compact designs, energy efficiency, and durability. These innovative technologies represent the next frontier in the quest to discover life beyond Earth. By overcoming the interference caused by starlight and enhancing our ability to detect faint signals from distant worlds, we are unlocking entirely new levels of precision in space observation. Future missions are already in the planning stages. NASA and ESA, the European Space Agency, are collaborating on the LUVOIR, Large UV Optical IR Surveyor, and HABEX, Habitable Exoplanet Observatory, telescopes. These missions are being designed specifically to search for Earth-like planets and analyze their atmospheres for biosignatures, the telltale signs of life. LUVOIR, in particular, will have a massive mirror and the capability to directly image dozens of potentially habitable exoplanets. HABEX, on the other hand, will pair with a star shade to maximize its ability to block out starlight and isolate the light of orbiting planets. The combination of high-contrast imaging and advanced spectroscopy will allow scientists to search for a variety of gases in these planets' atmospheres, such as oxygen, ozone, methane, carbon dioxide, and water vapor. The simultaneous presence of these gases, particularly oxygen and methane, would strongly suggest biological activity. In the meantime, the James Webb Space Telescope continues to lay the foundation. Every observation, every spectral reading, every thermal anomaly it detects brings us closer to answering the most profound question humanity has ever asked: are we alone? Public interest in these discoveries is surging. The idea that we may not be the only intelligent beings in the universe has long been a subject of science fiction, but today it stands at the edge of scientific fact. The lights detected on Proxima Centauri b, whether artificial or natural, symbolize the dawn of a new era in astronomy. And as we look further into space, we are not just searching for others. We are also seeking a deeper understanding of ourselves, our place in the cosmos, our potential for connection, and the extraordinary mystery of life itself. The journey is far from over. With every new telescope, with every mission launched into the unknown, we push the boundaries of what's possible. One day, perhaps soon, the faint light in the distance won't just be a mystery, it will be a message. Withstand the harsh space environment. Despite these challenges, the potential benefits are enormously positive. Observing and evaluating the environments of exoplanets may result in the discovery of chemical signatures in biospheres. Oxygen is one of the indicators of life. Water vapor or methane, specifically the ratios of these molecules, may indicate biological processes that suggest life. Researchers believe that life exists beyond Earth. Also, scientists are looking into direct imaging techniques to observe future distant worlds in greater detail. Telescopes may be outfitted with advanced adaptive optics that correct for distortions brought on by the Earth's atmosphere or the motions of the telescope, resulting in combined images that are sharper. With technologies that block starlight, these enhancements may make it possible for scientists to go beyond just finding exoplanets, enabling them to examine and map their surfaces and gain new perspectives. The growth of next-generation space telescopes is a significant advancement in our efforts to answer one of humanity's most profound questions: Are we the only ones in the universe? By increasing our capacity for observation, we are getting closer to determining whether life exists beyond Earth, with the potential to change our comprehension of our position in the cosmos. Furthermore, the search for life elsewhere is advancing at a rate never before seen, as astronomers and scientists delve deeper into the enigmatic worlds of faraway exoplanets. The James Webb Space Telescope is about to usher in a new era of cosmic discovery. It gathers data that assists astronomers in acquiring groundbreaking information regarding the structure and potential habitability of distant worlds, new information that brings us closer to answering the fundamental inquiry: is there life beyond our planet? Proxima Centauri b, the exoplanet orbiting the star closest to our own solar system, has been the subject of extensive research for years. But to this day, locating tangible evidence of life, such as signs of artificial light or civilization, remains a distant dream for many. The fact that such light has been found, even faintly, by the Webb telescope bolsters hope that we may one day communicate with intelligent life in the universe. Discoveries like these stimulate scientific interest and spark new ideas, inspiring generations to think outside the box. The James Webb Space Telescope continues observing, not just searching for synthetic lights but also concentrating on the atmospheres of planets, analyzing the chemicals within them, and studying how these elements might support life. The search for biomarkers such as carbon dioxide or methane in the right concentrations is necessary for determining whether or not these planets have the ideal conditions for life. The telescope provides the ability to examine these elements of planetary atmospheres in ways no other instrument has before, bringing to light the potential of distant worlds where life could flourish. One of Proxima Centauri b's most fascinating features is its location in the habitable zone of its star, where the right conditions might exist for liquid water to be present on its surface. This surrounding area, the Goldilocks zone, is a region around a star with just the right temperature, neither too hot nor too cold, where water can exist in liquid form. This is regarded as an essential factor in deciding whether a planet could support life, as water is vital to the development of life as we know it. The finding of an exoplanet inside a star's habitable zone makes it an important target for future missions. In addition to discovering life-sustaining planets, future telescopes will also study the complex interactions between exoplanets and their stars. For example, Proxima Centauri b is believed to be tidally locked, meaning one side of the planet always faces the star while the other remains in darkness. This could result in extreme temperature differences between the two sides, significantly impacting the planet's climate and its potential to support life. Understanding these conditions is crucial for astronomers as they evaluate the likelihood of habitable environments on exoplanets. The development of technologies capable of blocking out bright starlight is another major advancement in space exploration. Without the ability to isolate starlight, it would be almost impossible to detect the faint glimmers of light from distant planets. Star shade and coronagraph technologies, mentioned earlier, are excellent examples of how scientists are overcoming these challenges. By preventing the uncontrollable brightness of a star, these telescopes can use tools to detect the dim light reflected by planets, light that could reveal important information about their environments, potential, and surface features that may support life. An exciting new development in this field is the idea of directly exploring exoplanets with the aid of starlight blocking technologies and advanced adaptive optics. Astronomers hope to capture high-resolution images of planets as they revolve around their stars. These images would not only offer more comprehensive data on the planet's composition and settings, but could also provide deeper insight into surface features, such as continents, oceans, or weather patterns. This kind of imaging would be a significant advancement in our capacity to learn about exoplanets and make informed decisions regarding their potential to sustain life. As we move forward in our exploration of the universe, the answers to the question of whether life exists beyond Earth grow closer. The role of the James Webb Space Telescope, and future missions, will be essential. Its capabilities to detect faint, distant signals, study planetary environments, and examine habitability potential are changing our perspective on the cosmos. With ongoing technological advancements and a growing body of research, we are on the verge of discovering new information that could alter our understanding of life in the universe. These revelations carry the potential to redefine not only our scientific paradigms but also our philosophical and cultural perceptions of existence. The confirmation of life beyond Earth, be it microbial or intelligent, would mark a turning point in human history. It would challenge long-held beliefs about our uniqueness and could unite humanity under a shared curiosity about our cosmic neighbors. In preparation for such discoveries, space agencies and institutions around the world are collaborating on the development of next-generation observatories. Projects like the European Extremely Large Telescope (ELT), the 30-meter telescope, TMT, and the Nancy Grace Roman Space Telescope are expected to play pivotal roles in detecting Earth-like exoplanets and analyzing their atmospheres. These telescopes, equipped with state-of-the-art spectrometers, will allow scientists to detect the faintest of biosignatures, such as fluctuations in atmospheric gases that cannot be explained by geological activity alone. Moreover, missions focused on sending robotic probes to the icy moons of our solar system, like Europa, Enceladus, and Titan, further expand our understanding of life's potential. These celestial bodies, with their subsurface oceans and geothermal activity, present a different yet equally compelling scenario for habitability. As humanity pushes deeper into space, questions of planetary protection and ethics also emerge. If we are to explore or even colonize other worlds, how do we ensure that we don't contaminate potentially life-bearing environments? Conversely, how do we protect Earth from possible extraterrestrial microorganisms? The answers to these questions will require not only scientific rigor but also philosophical introspection. What responsibilities do we hold as explorers of the cosmos? And how do we prepare society, politically, morally, and spiritually, for the possibility that we are not alone? Ultimately, the search for life in the universe is as much about expanding our understanding as it is about finding connection. Every star we observe, every signal we analyze, and every planet we image brings us closer to answering a timeless question. Are we part of a greater cosmic community? And as our instruments become sharper and our reach extends farther into the vast darkness of space, the silence may one day be broken, not by speculation, but by the first undeniable echo of life calling back.